the wind is so bad up there, I couldn't close my car door for a second.
Look, I got the same number now.
Yeah, the wind was blowing so hard, I got hit by a rock. Yeah.
Well, you did get hit by a rock? Or oh,
yeah,
wow.
yeah, like a rock got picked up off the street and like hit my leg.
That's bad.
I guess it could have been
Ice.
it could have been salt, but couldn't tell the difference.
Hurt all the same.
Yeah, exactly.
All right, you wrote it. It's really good right here.
Yeah.
Kill that's what I have.
Things in now.
I have no idea what went on.
I heard you asking questions and I watched the video and I'm like, God, me too, bro.
There's thermo test today?
Thursday.
Thursday. Oh, you got time.
Well, there's no cheat sheet. He's given us an equation sheet that seems to have some holes in it.
It has all the balls.
Yeah, a lot of holes. We did today, we're going over one of our homework problems, and he's using equations I've never seen before.
I'm like, where did you get that? And he looks at me, he goes, I don't know. He's going to text me that twice. He's like, come out. I'm like, bro, pull these equations out of your butt.
Well, what time is office hours?
Officer, there's general health, and those two is Teresa over here. I know her, she's super helpful. And then Anatol, the officials here.
All right.
3 to 4? Yeah.
Cool. We're back. Quiz 1, hopefully that one, like even if you didn't do it, but no problems coming up, that's the plan. Submit that sometime today. Project 1 we were looking at on Friday, thinking about like what do you want to, where is this class leading? Like what is something that you want to learn or something that you want to talk about from this class? Next thing coming up is homework 2. Are there leftover questions from Friday? I didn't talk to everybody about like individual ideas for projects, but was there anything, either a general question or very specific? Yeah.
Well, for the project, as long as you have like the 3 questions answered and like little setup, the diagrams, like that, you're good to go for the project? Or?
Yeah, in terms of like assessing the project.
Like what I want to study as like a project.
Yep.
And then identify all the courses on the kinetic and the free body diagram.
Okay.
It talks about how what I was going to study could help my future career or something like that.
Yeah, yeah, that's great. So just kind of repeating for Mike and stream, like there were those couple of questions on the project, like how are you applying new knowledge, what are the basic, or well, you have basic definitions, so what's an example that you want to look at for career or hobby or just general interest, and then how do you apply, like how do you see this project applying to that aspect? Here, the more specific you get, the easier it is to work. I noticed like one thing on like our first discussion post, we were talking about, I asked like, what's a job that would ask for this class? And people had like general ideas of jobs, but not actual specific jobs. Like, what is a specific job that would require a dynamics background? And I think that's kind of like where you're at, is like a lot of things are generalities, but the more specific you get, the easier it is to look at the general picture, if that makes sense. I'm talking very big generalities, but rather than saying like, hey, Copilot or ChatGPT, what kind of jobs use dynamics? Come into LinkedIn. Oh, Ame. So yeah, so let's go straight into jobs. And then like if you look for a job that's looking for kinematics, that's usually like a job skill that people are looking for is kinematics, somebody. AI training. Oh, this one's all remote stuff. We don't want physics.
Physics expertise for 12 bucks.
Yeah, for AI. Those AI training jobs are like, they're ridiculous. They're
What do you even do? You just like tell it to fix itself?
I tried it because I was like, all right, let's see what we're up to. Product dev engineer, like that makes more sense. R&D modeling for cooling, infinite cooling, or solid mechanics consultant. There you go. Yeah, those AI jobs, they give you like prompt and responses, and then they ask you to like do further research for the AI tool to try to improve. But they pay you like by the hour, so it's ridiculous. It's not worth, at least for me, it wasn't worth my time. It's like, I don't know.
Maybe if you're going for a degree or you're studying that stuff, you might as well just answer some questions.
Well, like it wasn't so much that. It was like, at least the job that I tried, they gave me like 4 PDFs of like reference manuals for something, like, I don't know, like some kind of sensor. And it's like, is it true that this sensor does that? And you have to look through the manuals, and you find out that you have to go to the website, so you have to do the digging. And I'm like, that's worth $200 an hour, and they're paying like $12 an hour. So I'm like, all right, yeah, yeah. Abacus. This is looking for everything. FEA, ANSYS, and/or LS Dyna. Well, let's see what they're looking for. Ooh, do you know what DIC is?
Digital image collection?
Yeah.
Correlation?
Yeah, what do you use it for?
AI.
No, there's no AI in image correlation.
It's just like we can take a picture and then model it.
Sometimes you can use like 2 pictures and try to create a 3D image. Part of that is correlation, like taking images from 2 different perspectives and then combining it into a 3D image. Some of that's image correlation. For DIC, usually if it's like solid mechanics, image correlation, a lot of times you're looking for like images of something stretching or compressing, and now you can get strain across the surface of this object. Yeah.
Now, this is just pure curiosity. The CNC tool and cutter grind, what kind of experience do you need to do that? I would do that.
That one is probably mostly a lot of the stuff that we were first talking about, like kinematics, of just like, do you understand geometry and tolerances and those kind of things? And then there's like tool grinding ideas, which we cover a little bit in the class that's later on, like senior year usually class. Oh my god, what is it called? Well, Professor Mealy does like metal cutting principles, which would cover that kind of stuff. I think it's metal cutting principles. And then there's another one, but anyway. And a lot of that is stuff that you learn on the job anyway, so it's like, if you've done some metal work, then you've got a general sense of it. And then measuring things, problem solving, yeah. So definitely, so like in this case, if you were trying to say like, hey, I'm ready for a CNC tool cutter job, you could say like, I've been studying kinematics in this dynamics class. I'm thinking about like how motion and forces are related, which is the exact skills that we need here in your CNC to like bring it to the next level. Like that's your sales pitch from this class. Yeah, anyway. All right, cool.
It was not thermodynamically capable to have a shell.
All right, module 2, looking at constrained dynamics. A lot of this is like kinematics, like understanding geometry and constraints on motion, but we're also talking some about like how, if you know what the motion is, what are the forces involved? So which is kind of like a inverse kinematics problem. Like I know I want it to do this, so assuming that that all goes according to plan, what were the forces that I needed to create that motion?
What's a Grubler count?
What is a Grubler count? Sounds like something from like solar opposites, right? Yeah.
Not to like get to it, but I was looking at the reading, and I actually had a really hard time understanding the equations 8.5, 8.13, 8.21, like the notation. I don't think else like had trouble with that. I put it close in the GitHub list. I just don't understand what they mean.
Yeah.
I didn't want to like jump ahead too far. We would probably go over it. What is this? Like a mini stroke kind of thing.
This is, what chapter was it?
It was the equation you listed. 8.5, 8.13 is the transport equation. I don't really understand it. Or the way it's written, I guess.
Like 8.5, this one?
Yeah. Like what is the squiggly eye in reference to that frame?
Yeah, so we can take a look at that. Yeah, so what is this one? All right, so we're going to use I and, if we want to stick to I and B. Is that right? O prime slash O. And this one is B. I and B cross. I'm trying to get the notation correct. All right. This notation is a little strange, and so remember, I in the first homework, like some of the first problems, I had recommended like, all right, when you're writing vectors, try using unit vectors to start, and we're already this equation is kind of like why that warning message was there. Because now we're dealing, in this case, this equation is dealing with like, how do I understand velocity when I have a rotating coordinate frame? So like some of the classic examples are, at least like physics classic examples. Let's do this. Like you have an ant on a record player, and if you want to know the velocity of the ant, then it's a combination of where the ant's walking plus how fast the record player is moving, and that's what this equation is trying to get us at. This one is. So,
Is I always perpendicular to the ant motion?
I mean, in this case, yeah, but in general, it doesn't have to be. I was just trying to give us like a more concrete example
Okay, so what do you
of.
mean when you write
I is this rotating reference frame. So in the rotating reference frame, the ant is moving along one axis. And again, it doesn't have to be that way. Like the ant can do whatever it wants, but
like relative to the record, the ant is just moving in one, like along the x-axis of the record?
yeah, yeah.
Okay.
Yeah, so the record, like if the yeah, what's a good, say like that.
So if you had a camera that traveling, but the camera's spinning the record, that's how it would work.
Like it's always traveling along the text, Daft Punk. Yeah. So if the ant is always walking along that text direction, let's say it is 1 meter per second along that I direction, is it moving at a constant speed? It's good. That's a good follow-up question. Is it moving at that speed in that frame? So in the frame, constant speed. Okay. What about in general? Is it a constant speed? Yeah, bigger radius, bigger speed, right? If you're moving at a constant rate, but you're so two people, one person standing in the center of the record player versus the edge of the record player. Like the person in the center is not moving at all versus the person on the edge is now moving, whatever, r times omega. So even though our local spinning reference frame has constant velocity, velocity is not constant. But we have some acceleration. So that's what this equation is trying to give us. And yeah, how deep do we want to go on this? So I know this one is 1 meter per second along that I direction, plus 33 1/3. I don't know how many radians that is, though. (33) 1/3 RPM in 3.49 radians per second. Sounds about right. I don't usually like to trust AI math, but it's okay. We'll try it. 4? Oh, core. That one's also, you got to check your references. So what was it? 3.5? In that K direction. Crossed with, now its position, like RPO. Let's say it's like 5 centimeters along there, so like 0.05 meters. Oh, spin, yeah, sorry, I didn't even explain. So spinning is a vector. Its axis is describing where it's spinning around, and the magnitude is describing how fast you're spinning. So when we have like omega, if things are moving in a plane, it's always either a positive K, so positive, yeah, thumbs up, positive, spinning that way. Use your right hand rule, yeah. My dad in Naval Academy taking a physics test, and he saw, he wanted to like shout to this other engineering student because they were doing all their physics calculations with their right hand, or sorry, with their left hand, writing with the right hand. It's like, no, stop, use the right hand. Right hand rule, yeah. Positive, negative.
I mean, physics too is like 12 different right-hand rules and ones.
They're all, it's all the same though.
Yeah, but the vectors of like what you're talking about all flips a lot of different ones. I mean, right, depending on like if you're talking about like the direction of current or
Yeah.
I don't remember all of them,
But for the most part, it's just describing cross products, and cross products are always.
a lot of times like sometimes like you can use similar variables. So sometimes if you're like, oh, but this variable which is like b is up, but this other equation b is
Yeah.
straight, and you're like, wait, he's trying to remember.
Yeah, that it does get confusing. 3D stuff gets confusing pretty quick. So then we'll say like 0.05 meters along that I direction. So my total velocity is going to be,
Was 0.05 the radius of your gap, if I'm correct?
yeah, so like the ant, if it's at 0, if it's right in the center, it would be 0. If it's 5 centimeters out, now it's 0.05.
So
How big is a record?
Currently 5 centimeters out, or is the radius of that part?
That's it's whatever, so RPO is like what you're tracking. So P is our ant.
Okay.
Yeah. At least in this case, in this like little example. How do you do cross products? This is something that we haven't done yet. Negative J? Yeah. Okay. How do you know?
Oh, I just know that I know it's like this circular thing inside.
Yeah, all right.
Backwards, that's negative version.
Yeah, that's what I like to do for cross products is write IJK like in a circle. So if I'm moving that way, then it's yeah, positive and then negative if I'm going backwards. So K cross I is a positive J. So 0.05 times 3.5, what is that?
Oh yeah, I flipped the J in the camera.
Oh yeah, I always write it down just so
That's why I need to.
I don't miss it. Yeah. 0.5. I don't know. What is that?
J cross K is possible. K cross J. Wait.
Yeah, I thought I was the first two.
So that's what. At least for me, it helps to see like a concrete example of like what are these vectors actually describing. So in this case, we have velocity in the relative frame, that O prime O is just describing how fast am I moving in the rotating frame. And then omega and R, those are describing how fast the frame is rotating and where I actually am in the frame. So we did all this work to like plug those variables in. Another way we could have done this I could have said the position of the ant is radius r times ER, right? That's just where the ant is. So some radius, some unit vector, I don't know what it is all the time, but I can define it because I do know that it's going to be like x along that I direction. So it's in that, so ER is always in that I direction that I just chose. Velocity is going to be the change in R, so R dot, or dr dt. I like the dots because it's easier for me to keep track of stuff. Along ER. But now I have to take the derivative of ER because ER is changing, right? The magnitude of it doesn't change, but it does change direction. So that means that it is changing. And the value for that ends up being, so it's R times a theta dot E theta. Where E theta is like 90 degrees to ER. And now we have the same equation. We'll end up with the same result that we got before, where we had 3.5 times 0.05. That is R times theta dot. So sometimes it makes sense just to use like cylindrical coordinates rather than like trying to fit it back into this equation 3.8. Is that right? Kind of cool. Different way. There's usually more than one way to approach things, but yeah, and these like rotating reference frames, they can get a little confusing, and a lot of times you can avoid them. Not always, but at least in this case, we could. And we get the same equation. V plus, so here ER is that I direction, J is that E theta direction, so R theta dot in that J direction. That's a dr dt, so a dot is always like time derivative. Nice. Going hard to start module 2. Yeah, with some Daft Punk. We're up all night to get lucky. All right, so let's look at another like spinning kind of problem. Now instead of a record, well, it looks like a record, but instead of a record, we got like a flywheel. So we're going to use 2 cords to kind of yank this thing up to speed. So we know how fast it's accelerating, and then we know how heavy it is and how big it is. Can we figure out how much force it took to create that acceleration? This is that inverse dynamics problem that I was talking about. Oh, that looks terrible. Oh, there we go. All right, so how do we start this up? What do we do with this information?
You should write down all of our known values and free body diagrams. How many do you know free body diagrams? Why not though?
Yeah, I like it. So free body diagram, separate out known values is always a good start. What are we working with? So what does it look like?
Yeah.
Yeah. No, because it's just kilograms times meters squared. Yeah.
What's the, do you feel like it's guiding you? Okay. Yeah. What's it telling you to do?
Well, there's no camp on the record, like,
Okay. Yeah. Thinking about like 3 different steps of like, so taking like one place and splitting it up in 3.
Yeah.
Okay.
And the first question I kind of found about just things around the friction or split.
Okay. Is that applicable to like flying or?
Well, that was first question was like,
Okay. Yeah. So just like general.
you know,
Okay.
general overview of what we do.
Okay. Cool.
I just wanted to make sure it was.
Yeah. I mean, you can like if you get feedback, you can always reason it.
Okay.
It's been,
Yeah.
if it's not moving.
this is a final accelerator. So it's,
No. I did all the reading.
Yeah, so since it's negative, it's spinning that way. If it was positive, it would be again.
How does the inner radius matter? Who knows? How does not a rhetorical question matter? There's no hand.
No, yeah.
You know what I mean?
Yeah.
Like you can't that term's 0. I think. There's no hand.
Yeah.
We also aren't given inner radius. Does it matter? Probably not.
This one, like if we know moment of inertia, that's more important. At least for this one.
Just in case some people forgot, moment of inertia is useful for which thing?
Yeah, what is moment of inertia? Like why? What? All things? All things?
Well, we learned in statics, and then the professor's like, you won't need this.
Yeah, I think you learn moment of, man, is it moment of inertia or moment of area? Because there's,
We learned moment of area and then second moment of inertia, so I know we get.
yeah, so I think this is second moment of inertia. Moment of area tells you like how much distributed mass across the cross section. So that one's usually like meter to the 4th power.
Yeah.
This one's going to be like a kilogram meter squared because it's telling. And roughly you can, one way to think about it is like your mass is like the average. Like on average, you are a certain scalar value of like how much mass is right at the center of your body. The moment of inertia is telling you like how spread out is that mass. So a really large moment of inertia for the same mass means that it's really spread out, like stuff everywhere. What would be a moment of inertia of 0? What has like 0 moment of inertia?
Would M or R have to be 0?
Yeah, if m is 0, then it's 0. So photons, they have no moment of inertia.
So just photon.
Just photons. Yeah, what has 0 moment of inertia?
It's just M.
mr squared. Most of the time it's like mr squared, like something. Sometimes it's 2/3 mr squared. Sometimes it's like 2/5, or it's always some kind of factor. Or like could be a squared plus b squared for rectangles.
If it has mass, it has radius.
Well, it's just, if it's only radius 0.
Like in the first module, we dealt with 0 moment of inertia a few times.
Pulling out the center of gravity.
Because anytime you make a point mass assumption, you're assuming I is 0. Yeah. So if I is 0, then yeah, maybe it is spinning, but it took no force to actually spin it. No torque. All right, so I've seen people kind of draw like givens out. And roughly we could say like this is the start of our free body diagram. Are there any other forces acting on it? On this? Here, let's just draw forces, right? F. Anything else? You could think about gravity, if you want. This thing is really like it's fixed right in the center. There's some kind of like rotational thing. So it's not going to change, like it's not moving up or down. So if we think about that there is gravity, then there's also like some kind of normal, like keeping it up.
You could assume there would be no friction between the axle and the flywheel, right?
Okay, yeah. Yeah, we could say that there's no like resistance to, no like torque resistance. All right, we could start here. What does the kinetic diagram look like? Is it moving forward or backward? Like, is it moving left or right? It's just spinning. Spinning in place. So it's not moving up or down. It's not moving left or right. So it's just spinning. How do we describe spinning momentum? Yeah. I alpha? Yeah, yeah. And I'm like maintaining a right-hand rule positive kind of thing here, just so we have the same, just to maintain consistency. If you can keep track of flip-flopping vectors, then it's okay, but I'm just using right is positive, up is positive, counterclockwise positive.
Why do you multiply I by alpha?
So second law says F equals MA, or F equals the change in MV, like this, which if I do like R cross F, not really changing Newton's second law, but now I can start to talk about like how does moment get involved with this kind of problem. So then it's R cross ddt of mv, and there's a little bit of like magic arrow, some magic that happens, but what we end up with is that R cross F equals the change in R cross MV. And that RMV is angular momentum, and angular momentum is I times theta dot. At least for two-dimensional kind of stuff. Like if something's rotating in a plane, then angular momentum is described with like some kind of value of moment of inertia times how fast it's rotating. And if it's changing, now we have I theta double dot. That's telling you how much your angular momentum is changing. So that's where we're kind of getting I alpha is like a theta double dot. Yeah.
On the last line. With the bar over it, what?
Oh, H.
Okay.
Yeah. So like angular momentum is H, and H is I times theta dot. Oh, dots are like d dt. It's shorthand for writing out like a d over dt for variable. And it's a total derivative, not a partial derivative. Little d, not a cursive, like a kind of mini delta. Cool. So if we have a free body diagram, we have a kinetic diagram, we should be able to sum the forces along the x, sum them along y, sum them along the moment. Like, what are the moments acting on it? So what do those equations look like? So what are the forces in our free body diagram? What are those? Yeah, it's not moving, so it's not zero.
It's also not moving a lot of it. You do have a big moment, but I guess you want to start with say the moment about what's the radius that's sitting out? 0.1. 0.1 meters. Which way is positive? Which way is quick? Which way is clockwise? Spirit told me clockwise is negative.
Yeah.
No, it's not. I don't care. It doesn't actually matter.
I know it doesn't.
As long as you define it.
Which is why it's silly. Because time moves forward. Why would forward be negative?
Like positive this way, positive this way.
The reason is because of the right hand. The reason is because of the right hand rule. That's right. Because if you have counterclockwise, it's good for left hand. Dude, I'm saying, if you're a pirate and you're in physics, you have put on like a little, orthogonal thing. Just
That one is telling you that if they have positive acceleration.
dude, I'm so concerned with I'm so worried about
I've not talked to a single person that's like,
look, I hate them all. I'm pretty good. I'm not going to sugarcoat it. I feel like this is a great cycle. This is how every jet engine ever works. Alright, class is over. Smiley later.
he went over 4 cycles. That's right, guys. It's on the exam next week.
And his equation sheet's not complete. There's no MEP formula.
There's a lot of missing things out there. There's no ideal gas relations almost at all, which is, I can figure it out, but
Like, I don't want to have to drag this. Yeah. Also, can I ask you, like, please don't make us interpolate during the exam. You'll waste time. If you make me interpolate, I'm going to take the closest table value.
yeah, I'm Yeah, I think sometimes tables would be moved.
Yeah, how are we getting?
He's only, if you do efficiency, he should only give us the relevant for torque.
I just, it's gonna go horribly, he's gonna, next class he's gonna give us a regular cheat sheet on every other class.
Yeah, I don't know, man.
Yeah, right.
I talked to Anatol a couple of times.
Yeah, but okay, there's so many problems, like, okay, there's so many problems differently than I saw online, that I tried to do myself, different than the equations I've seen. From the book. Exactly, you know, we had these equations in the book, I looked over the entire chapter, it's not there.
No, I did understand where one of them came from, with denominator like V1 minus V2. You factor out the V1, and then you have 1 minus the reciprocal fraction ratio.
No, I get those, but, well, okay, also.
When do you use U and when do you use H? Like, what's the deal with that?
Well, I don't want
It's super arbitrary.
I thought you could use, temperature values, so like, I think it's, what is it? It's like specific heat times, like, changing temperature.
Yeah.
Use something, but they never solved it that way, and why did they compare everything to, reduce pressure and volume when it's not simply ideal, because you don't need to do that.
I think that part just saves time because you can get reduced values from the table.
It can, but we never really go over there.
Yeah.
All right.
We don't go right.
So we need our,
That's like my favorite subject there. No, it's a mixed bag. Did you guys get 0.2 passes for the moment? Because I took the radius to be 0.1 meters because that's what you got negative? Oh, it is clockwise. I was literally just yelling at Mike about clockwise, and then I wrote it as counterclockwise. The self-awareness is not strong.
all right, so let's stop and do a moment. Do we know how to calculate a moment? It's torque, yeah, it's torque. But do we know what we're talking about? Yeah.
That was a really level joke.
Let's say this is 3i plus 1j. F is meters. F is going to be 2i plus 2j newtons. How do I get total torque created by that force F applied at that R? So R cross F, right? R cross F. So R cross F is moment. And a lot of times as engineers we talk about torque. Torque and moment are kind of interchangeable. Torque is like magnitude of your moment. So moment is very much a vector, has a magnitude, has a direction. Usually it's like the same idea as spinning. Like the torque is describing the axis that it's rotating, that it's being applied along, around. So if I've got these two vectors, take the cross product, now I've got I cross I, 6 I cross I. What is that? Zero. And then a 6 I cross J plus 1 times 2 J cross I plus 2 J cross J. So what's I cross J?
I cross J is K.
K, yep. What about J cross I? Negative K. And then J cross J? 0. So now I've got 6 minus 2 K equals 4 Newton meters along that K. Cool? All right, so now that we did our moment, how do we figure out what the moment is from that top force? We did a hard problem, now we have the easy one. They're perpendicular. That one's nice, yeah. So it's R times F, yeah. Positive, negative. Yeah.
Why is I alpha spinning in the opposite direction of the flywheel?
The flywheel is definitely going to spin. So really what we're doing here, and that's what I was asking, do we have a positive or negative moment? Because we're creating a negative moment. So the flywheel is going to have a negative alpha. And that's what we have here. It's like alpha is negative 50 radians per second squared. If we applied the opposite forces, then we'd have a positive moment. Alpha is positive, it's spin, but yeah, it's gonna spin with those forces. Are we out of time? I don't want to keep everybody. All right, this has been fun. We'll come back better and stronger.
So for the project, this looks okay? I just have like...
Yeah, I'll take a look. Nope, what happened?